Uh, okay, so welcome to class 9, where we'll be discussing some more properties of S equal to kb log omega, just to check that kb log omega has the right properties of entropy. So in the last class, we discussed that when two isolated systems are brought into contact with each other and heat exchange is allowed, energy flow is allowed in the form of heat, the condition for equilibrium would be when the temperatures of the two systems are the same, and temperature, or rather 1 by T, was seen to be equivalent to del S del E. Right, with the number of particles and volume remaining constant. Now, if we allow both heat exchange, energy flow, as well as suppose we allow the boundary condition or the size of the boxes or the volume of each of the element of the isolated systems to interchange, what would be the condition of equilibrium? So that's one thing we are going to do, and then we are going to do so we have been talking about S equal to kb log omega. Can we explicitly calculate omega, at least for an ideal gas? And if we calculate that, can we derive the gas properties? So these are the two topics of discussion for today's class. So without much ado, let's go ahead. So we're going to discuss ideal gas entropy and derive equation of state, and also check that kb log omega has properties consistent with that of entropy, right? So what we did in previous class, just to remind you, that there were two systems, isolated systems, system S1 and S2. They were brought in contact, energy exchange was allowed, and the question we asked that after energy exchange has taken place, so that system S1 has suppose E1 dash instead of E1, and system 2 had E2 dash instead of E2, what would be the new values? What are the conditions for the equilibrium? And what we said that the total number of microstates for the two systems combined, which before energy exchange was allowed, was omega 1, function of E1, and of course N1 and V1, and omega 2 E2, and of course function of N2 and V2. So after energy exchange is allowed, the total number of microstates accessible would be more. So it would evolve to a new equilibrium. It would evolve to a new values of E1 and E2, such that the total number of microstates omega 0 dash. So omega 0 dash would be omega 1 E1 dash, because a different number of microstates is accessible to system 1, and a different total number of microstates is accessible to system 2. So so this would be the new total number of microstates, and that would be maximized. And we therefore put in the maximization condition with respect to E1 dash, and from that we got del E1 del E1 log of omega 1 was equal to del E2 log of omega 2, and that was the condition for equilibrium. And these things, with the appropriate multiplication of kb, was identified with entropy, and this entire quantity was identified with 1 by temperature. So we're going to do a very similar analogy where we have two systems in isolation, N1, V1, E1, and the other system is N2, V2, and E2, characterized by N2, V2, and E2. And now these two things are brought in contact with each other. They're brought in contact with each other in such a way that the volume can change. The volume of each system can change, keeping the total system S1 plus S2 isolated. So if it was initially V1, V and V2, it can now the total volume of the system will remain fixed as V0. So V0 was V1 plus V2, and V0 remains V1 dash plus V2 dash. Moreover, we are allowing energy exchange as well. So N1 and N2 are fixed, but energy and volume can adjust itself to reach a new equilibrium. And if they are in equilibrium, we know that if energy exchange is allowed, then T1 is going to be T2. But what is the new values of V1 dash and V2 dash, such that a mechanical equilibrium is also achieved? The system is going to interchange the volume or number of microstates which are accessible due to volume and both energy. So if you want to visualize that, you could think that let the system first adjust itself, adjust its volume, and we are again going to assert that the total number of microstates accessible to this combined system goes to a maximum, with the background that we will are going to associate that new number of total number of microstates accessible to the total system, we are going to associate it with entropy, right? So if we allow energy exchange, thermal equilibrium will be achieved when T1 equal to T2. But remember, when there is volume change, there is also some work done. One of the systems is going to do work on the other system, and that's going to get heated up. So if you like, you can first allow that to happen, and then allow appropriate energy exchange so that thermal equilibrium is also reached, right? So it's a combination of both. You can either do one or the other, or in a combined way, but basically you are allowing energy exchange as well as volume exchange between the two systems, keeping the total volume of the combined system fixed. So volume, what we are doing is, let's assume we have adjusted both are getting adjusted together, because work done, energy exchange, work done, energy exchange, and so on and so forth. But we are basically now primarily looking, we suppose the system has come to equilibrium, T1 equal to T2, what will be the volume? So what we are saying is the volume V0, which is V1 plus V2, can adjust to V1 dash plus V2 dash. And these two, so V1 dash and V2 dash are not independent. V2 dash is equal to V0 minus V1 dash, and exactly like we did before. So what is the total number of microstates in this combined system? When does it maximize itself? When does omega 0 dash is maximum? And now we maximize this with respect to del V1. We assume that energetically it has already come to equilibrium, though it will happen in parallel. And now we are going to take or maximize omega 1. So this omega 0 dash. And just like before, we are going to get del V1 log omega 1 equal to del V2 log omega 2, where I have dropped the dash again, just as previously, because so if you like, this will be V1 dash, V2 dash, but I'm just dropped it from the entire equation. So V1, V2 has become V1 dash, V2 dash. These are the new values of the volume where dash has been dropped for convenience of simply writing. And this is the condition for equilibrium, mechanical equilibrium. Volume, what is the new values of V1 and what are the new values of V2? So that will be arrived at when this condition is satisfied. And now we're going to look if we associate, so multiply both of the entire equation by KB, and then KB omega 1 is, if we associate it with the entropy of system 1, and KB omega 2, if we associate with the entropy of omega 2 of system 2, then we can see, and comparing with thermodynamics, so this is the statistical condition. And now if we look correspondingly, if we want to have a mapping, and if we believe a KB log omega 1 is the entropy of system 1, then we compare with this equation. So suppose energy has already exchanged and temperature of the two systems are the same. So then TdS equal to du plus PdV. If du is not changing, internal energy is not changing, if they have already reached thermal equilibrium, then del S del V at constant U T is essentially P by T. So del S del V is P by T, right? So if this is equal in the two cases, in the two systems, it also means that P by T is equal in the two systems. T, because of thermal equilibrium, is the same, and thereby the pressure in the two systems is also the same. And that is what we already know from thermodynamics, right? So just to repeat, if we identify KB log omega as entropy, we get the condition for equilibrium, mechanical equilibrium, is del S del V1 equal to del S del V, del S1 del V1 equal to del S2 V2 del V2, and that is P1 by T and P2 by T2. And if temperature are the same in the two cases, then pressure also has to be the same. So that is the condition for mechanical equilibrium. And now taking KB log omega seems to be more justified. It's at least consistent with whatever we are observing. Similarly, in a very similar manner, if we also allow the number of particles to exchange between the two systems, and we say, okay, the number of particles can exchange, volume can exchange, and energy can exchange. What is the new equilibrium? Then the TdS, when you allow particle exchange, is actually modified in this manner, where I'm using this minus is a Patria convention. And actually this entire thing is basically Patria section 1.3, and very identically you allow your energy to equilibrate, you allow your volume to equilibrate, redistribute itself between the two systems, and then an additional condition we'll get is del omega 1 del n1, del omega 2 del n2, right? And this quantity, I mean, of course, you multiply by KB, associate KB omega 1 with entropy of system 1, KB omega 2 with entropy of system 2. And then if you take del S del N, you are going to get mu1, the chemical potential by temperature, equal to chemical potential by temperature, and T1 and T2 is the same. So the chemical equilibrium, or if you like, the way the number of particles will distribute itself is also when mu1, chemical potential of system 1, and chemical potential of system 2 is identical. So if all three can be exchanged, then T1 has to be equal to T2, mu1 has to be equal to mu2, and the pressure of the two gases have to be, or the two systems in general, we have not talked about gases, they have to be the same. And thus, if we take KB log omega and associate it with entropy, things are simply consistent. The question was asked in class that how come that somebody could think of S equal to KB log omega. So we'll address this in the next class after we discuss Gibbs paradox and so on and so forth. Okay, so going ahead, so that we'll address that question, because that's I mean, how did S equal to KB log omega suddenly pop up? How did Boltzmann have this intuition? So we will postpone this discussion to a later class. But going ahead, what we can see is what we saw, that P by T was del S del V at fixed N and E for each system, right? And now this can be written as, so 1 by T in turn can be is del S del E at constant N and V, right? So that's what we showed. The condition for two systems to be in thermal equilibrium is when del S del E at constant N and V is identical, and then we associated this del S del V with 1 by T. So all that I'm writing here, so I've taken this T on this side of the equation, and then T is 1 upon del S del E at constant N and V, which for partial derivatives, I can write it as del E del S. Basically, I've taken this, and that's true because it's a partial derivative. And now what you have at constant N is fixed anyways, what you have is SVE, ESV, and I'll just remind you of the chain rule of partial derivatives, from which we get P equal to minus del E del V at constant N and constant entropy. We're going to use this relation in a few steps when we calculate the explicit form for omega for an ideal gas, which is the next topic of discussion. And similarly, using a similar very chain rule, one can get that mu equal to del E del N at constant V in constant S. So what does this chemical potential mean? So how does energy change as you change the number of particles? But that has to be done at constant V and S, and that's extremely important. So basically, you can think that you have a box if you are thinking computationally or modeling wise. I mean, anyways, so you add a particle. Chemical potential is a measure of how much the energy changes as you add one more particle. But remember, it has to be done at constant volume. Boundary conditions you keep the same. Okay, the box size you keep the same. But it has also to be done at constant S. Entropy must be unchanged as you add the particle. So number of microstates should also remain unchanged. So one has to adjust the E value, the total E of the system accordingly, so that the number of microstates remains unchanged. So it's not just about take a box of particles, add another particle. If you add another particle, its energy will also change, right? But then its entropy will also change. No, so that's not how to do it. So you want to look, when you add a particle, how much does the system change, keeping the total number of microstates unchanged, so that entropy remains unchanged. And that is the meaning of chemical potential. It's not just about adding another particle. You adjust the energy as well, so that the total number of entropy, so that the total number of microstates remains the same. And then, so you measure del E del N, keeping that condition intact. So it's a bit more tricky. I want you to keep that in mind, and hence calculating the chemical potential even in a simulation, and many of you are doing the computational physics course, is much more tricky than calculating other quantities like pressure. So the one has to, never mind what one has to do in a computational physics course. I mean, we are going to not cover it anyway. But yeah, so that's what I want to say. Okay, so we have got a mapping. If S equal to KB log omega, In general, the thermodynamic properties seem to remain or seems to remain consistent in terms of energy exchange, mechanical uh, change in the system, keeping the total volume of the system unchanged, and so on and so forth, and also in terms of chemical potential. But obviously, this omega is a very abstract constant with a phase space and so on and so forth, right? It seems to be an infinite system. Can one calculate it so that one can see how the functional form of omega looks, and can we really calculate S from the microstates? So this must be a question which is going on in the mind, and this is the thing which I'm going to address next. So changing a bit tack. So this part is taken from Huang, chapter 7. I'm not continuing with Patria because it has given much more details and quantum statistics. So this becomes a bit diffuse. I wanted to just somehow quickly give an intuitive idea of how to calculate this omega, and this is better done in Huang. So what you already know that we are going to calculate omega for an ideal gas, and for an ideal gas, the Hamiltonian is sum over all particles and different directions, degrees of freedom, momentum square by 2m, assuming the mass is of all the particles is the same, and we neglect the potential energy. We have only the kinetic energy in the expression for the Hamiltonian, but at the same time, remember that if you had an ideal gas and it was completely uninteracting with it with each other, then these particles would keep on going in straight lines forever, right? You wouldn't have any boundaries and so on and so forth. So there are collisions, else it would never thermalize. If they were completely uninteracting, whatever were the initial velocities of the particles, it would remain so. But when we say that we are having an ideal gas, we mean that there are collisions, so there is momentum exchange, but the potential energy is not contributing to the Hamiltonian. Those are instantaneous collisions, and potential energy is not contributing, and hence the Hamiltonian is just the sum of pi square by 2m. Okay, so it is in this sense that it's an ideal gas, sum over 3n momentum coordinates. And the question we are asking is, what is the total number of microstates? Now, the phase space volume and the total number of microstates is also equivalent to asking what is the phase space volume of the system. And why is that the same? So what we have done is discretize phase space volume. So you say that you can measure the precision of measurement of x is delta x, and the precision or of measurement of p that you can distinguish is delta p. Okay, so this is an arbitrary quantity. These are arbitrary quantities in classical stat mech. So we say that, okay, we are going to say that x is between x1 and x2, and that's one microstate. Another microstate is when a particular particle is between x2 and x3, and that is all that we can do. So that's our unit, if you like, of position measurement and momentum measurement. And then we say, okay, within this, how is the system evolving? What is the total number of microstates, and what is the volume of phase space? And since there is some unknown factor of energy, I mean, even in the momentum, we say that the phase space volume is between E and E plus dE, right? So it can vary a bit because each particle's momentum is not precisely known. It's between P and P plus del P. So it has a certain range, and we are really checking out what are the values of so what are the different values of the coordinates? When I say coordinates, I mean x and v, that the system can take, the ways it can redistribute itself, and as the system is moving through phase space, what is the volume of this phase space? By the way, the delta x delta p, and it has more whole cube, because for each particle, assuming 3D. Here we are calling it h, but it was later realized that h was Planck's constant. But that experiment had to wait quite a few decades before this realization was fully made. But here we are saying, oh, okay, we are just take that, we'll just count how many cubes in phase space, right, for each particle, and you can do it for n particles. In how many ways can the particles distribute its position and momentum, and it moves around, and how many cubes is the entire phase space made up of? So hence I'm talking about volume of phase space, which is equal to the number of microstates. So now there's an idea that of Liouville theorem, which I'm going to derive after a few classes. And it says that for an isolated system, the density of phase space points, the density, so you have a phase space volume, and within each region you have some number of phase space points. The system goes from one region to the other, but within each region, if you took a relatively large volume in phase space, the number of points available, number of microstates available within a phase space volume is fixed. It doesn't change as you explore different areas of phase space. If you considered the density of phase space is like an incompressible fluid, so at every point the density of phase space points is the same. Yeah, so it's not that some regions there are many phase space points, and at some other regions there are lesser phase space points. It is uniformly distributed. The density of phase space points is the same, and that is true for an Hamiltonian system and for an isolated system, not in general. But we are looking at Hamiltonian systems only. And in that case, since the density is uniform all over, all that we need to know is to calculate the volume is divide, so you're basically discretize the phase space in terms of h to the power 3n, right? So your basic unit is s to the power 3 of n. You're asking how many ways can positions of n particles readjust itself. What is the range of values of q that are allowed for each particle? So each particle can explore the entire volume. You are assuming point particles. You're not assuming that one particle. So each particle is a point. They can come arbitrarily close to each other. Yeah, and what are the momentum values allowed? What is the entire range of momentum values allowed? But the momenta have a constraint. The sum of momenta has to be the total energy, right? So we are really asking what is the what are the values of q1, q2, q3, etc. allowed? Over what range can it vary for each particle, and what is the range that P1, P2, P3 can vary, keeping the total energy fixed? And that is the volume of phase space, and that is for a classical ideal gas. But here in the classical ideal gas, when it was first done, I don't know when which decade, people didn't know about indistinguishability. So if one particle was here and another particle was here, they would consider it to be a different state, different microstate, if they were interchanged. So this is a different microstate. But we know from quantum mechanics that one is unable to distinguish whether the two particles are here or like this, right? And if you incorporate this indistinguishability of particles, then you would have n 1 by n factorial. So I have written this in red because the correct value of omega would have to take in this indistinguishability of particles, right? Because you can interchange various kinds of particles in different ways, and that would give an n factorial. But this was, yeah. So if you don't include this, you would have an inconsistency when you deal with gas laws. And we'll show that in the next class. Okay. So, but I'm writing this because this is the correct one. And it was plugged in classical mechanics, though they didn't know the reason. It's only after 20, 30 years that they knew that this factor appears naturally, or would appear naturally in the expression for omega, the total number of microstates of the phase space volume. But I have kept it in red. But initially, we're going to just do the calculation with this blue part, which is the classical ideal gas, the number of microstates calculated for a classical ideal gas. Now, remember when you explode, when the particles explode different values of momenta, and they're allowed a huge range, as long as this is kept constant, this constraint has to be maintained. And if you notice, this is essentially the surface in a 3n dimensional sphere. Right? So this is the surface of a 3n dimensional sphere. This is the equation of a sphere, if you like. So if this condition, I mean, except that it's in n dimensions, right? So x square plus y square plus z square equal to r square. So that is corresponds in 3D to all the points on the surface of a 3D sphere. And it's very similar to that, except that you have many more dimensions here. You have many more, yeah? So it's a sphere it's the surface of a 3n dimensional sphere, and we have to integrate keeping this constraint in mind. So when we say that we are calculating the phase space volume, we are essentially integrating over all real space coordinates, where each particle is allowed to take any of the positions allowed within the volume. So for each particle, if you integrate over the allowed configuration space volume, it will give a V. And if there are n particles, and this is it, I've written a D3, right? So this is easy. It will give V to the power n, volume to the power n, right? Because each particle can explore all the volume which is available, whatever be the shape. Actually doing it mathematically might be a problem, but just take it a cube, and when but whatever be it, each particle can explore the entire configuration space, the entire space which is available to it, right? On the other hand, this has to be integrated keeping this in mind, 2me. So 2me, if you like, is like the radius square. So the radius of the sphere, 3n dimensional sphere, is 2me. This constraint has to be maintained. And doing a bit of mathematics, so if you have a 3-dimensional sphere, the volume goes as r cube. If you have a circle, the area goes as r square. Similarly, in an n-dimensional, 3n-dimensional sphere, the volume will go as r, and r is 2me, to the power uh, 3n. Yes, r to the power 3n, right? And this is a prefactor like 4 pi by 3 or pi in 2D and so on. So this can be written as C3n because there are 3n degrees of freedom, 2me because r is 2me to the power half, and hence you get this factor 2, 2me 3n by 2. Okay, where C3n, and there's a 3-4 lines of mathematics where to play around with gamma functions and integrals and so on and so forth. This has been can be easily mathematically proved, but I want to focus on the physics. So this prefactor can exactly be calculated to be pi 3 to the power n by 2, 3n by 2 minus 1 factorial, right? These are just done in 3-4 lines in Huang. But I don't want to go into mathematics because I want to keep the focus in calculating the value of omega. Okay, so just take it and you can derive it if you want. Open the right chapter and derive it. So we have, so this is what I want the focus to be on. The total volume of phase space equal to v to the power n, which is coming from, it has dimensions of L to the power 3n. And this is the total number of microstates. So you have S to the power 3n factor sitting there. It has to be dimensionless, right? So this entire volume has been made also dimensionless by S to the power 3n. Some h has units of angular momentum. And from the momentum integral, you get C3n 2me 3n by 2, and have kept the 1 by n factorial, which would come in if we consider indistinguishability. So this is from the momentum integral. This is the unit volume of phase space to the power 3n, and this is from the volume integral. And then S by kb can be written as log of omega, and omega is a dimensionless quantity. It is ln, this constant. This is a constant quantity because it didn't really depend upon the volume, on the energy. It just depends upon the degree of freedom, right? N, it is independent. But if n is kept fixed initially, I mean n is kept fixed for an isolated system, we are calculating entropy for an isolated system, then we have an expression of the entropy which is log omega log C3n upon S. So this is a constant factor, n log v, because when you take the log, n comes ln of v, and here you get 3n by 2 ln 2me. And if you took the log of this factor, I have written it in red, ln n factorial. But at the moment we are neglecting it. Okay. So the next step is, okay, again, if we associate this quantity log omega or kb log omega to be entropy, then we know that if we take the derivative of E, it has characteristics of 1 by t, taken at partial derivative taken at constant volume and constant n. And since now we have an explicit form of omega and hence of S, which is this blue colored thing, and ignoring the red colored thing, you take a derivative with respect to E. This is a function of E, V, and N, right? N is also sitting here. Take a derivative, keeping V constant. So all that you have is, when you take the derivative, 2m by 1 upon 2me, taking a derivative with respect to E. So what you have after cancelling the terms is, and that thermodynamically is 1 by t. So t equal to 2 by 3 E n by kb, right? You can just check it out. Just So what I've done is take the kb here and so on and so forth. And then what do you get? You get E equal to 3 by 2 nkbt, which is the kind which you might already know, right? But here you are getting it from statistical mechanics. It is another matter that the value of kb was not known. But if you knew kb, if you knew the experimentally determined kb was determined experimentally, right? You didn't know what would be the Avogadro number. So it was discovered experimentally. It was discovered or measured experimentally. And if you knew it, then you would know that the energy in an isolated system would relate the temperature in this way, right? So you have got this relation starting from an expression of omega just by taking the derivative, associating ln omega with entropy, associating del S del E by 1 by T because it had the right properties, and the rest of the things simply pops out. It simply popped out. It was just a consequence of taking the derivative with respect to E. One step more. If you know this E, then you can take del E del T, and that is 3 by 2 kBn, and that's the heat capacity for an ideal gas, monoatomic ideal gas. What else do you know? You also know that if you take the derivative of entropy with respect to volume at fixed E, and again you have an expression for S, log omega, this is a constant. You're going to take a derivative with respect to volume, constant E. So ln omega, if you take the derivative, it will give you 1 by V, right? And that is in that case, so if you write del S del V, that is kb n by V. But del S del V at constant E was also P by T, thermodynamics. So you get this relation. And what pops out? PV equal to n kBT. You might not know the value of kb. But in hindsight, in 2022, you know it. And this is a very familiar equation. So you know that PV and T are related. And this is a constant in front if you have one isolated system of gas. And so basically, just by taking S equal to kb log omega, omega being the number of microstates, you are able to get back PV equal to nRT, and things are consistent with each other. So I'll stop the class here because I think you need to chew on this a bit. If need be, re-listen to it, and I'll continue in the next class.